So good evening everyone, let us get started. So last day we recapitulated the four types of induced EMF, that is first due to variation of current of its own winding, that is variation of self flux linkage due to its own current. There will be some induced EMF that can be represented by simply an inductance. Then we discussed about the variation of mutual flux linkage. In both the first two cases, the nothing really moves, so it is statically induced EMF. So first one, it is due to its own current, so that can be represented with an inductor. Then next one, it can be represented by mutual inductance, uh, what is so similar to a transformer. So both these cases are called as these induced EMFs are called as statically induced EMF or a transformer EMF, because in transformer nothing really moves, and the phenomena can be modeled by putting an inductance or mutual inductance, either self inductance or mutual inductance. Now, then the third case that we discussed uh, with certain depth last week or last class is what happens if self inductance itself varies due to some rotation, due to some movement of a body which is moving. So some rotor, in case of rotating machines, if it moves, then if the inductance itself changes, then even for constant current, we saw that the self flux linkage itself changes. And because self flux linkage is nothing but self inductance into current, so if current is constant and self flux linkage is varying, that means inductance is varying, and inductance variation causes that, and that causes some induced EMF to be there. And we saw that in the rising portion there will be some positive induced EMF, and in the falling region there will be some negative induced EMF. And if this is our physical winding, then of course this there will be some resistance of the winding, so IR drop, and there will be some induced EMF, that is E. And this induced EMF E for this case will have two components. One is some LDI term, that is there will be some inductance which will be dependent on the rotor position, and there will be some L into didt drop across that inductance. And apart from that, there will be a induced EMF, which will be this induced EMF, say what I called as E1 last week, that is basically I into 2L to theta into omega. So there is some current I flowing through it, so this one will have some voltage L theta didt. So there are basically two components. This is the total voltage applied across that winding. So winding will have certain resistance. So this is how we can represent such windings where the self inductance itself varies. Then we saw the case for mutual inductance variation, and we saw that the current of the winding does not is constant, and so is the flux linkage of that same winding, but of a different winding, which is actually moving with the rotor. As you can see here, the blue color winding that is moving with rotor. So although the current and the flux produced by the in coil 1, that is constant, the flux linking the second coil or the blue coil is actually changing with rotor position. So because of that, there is some psi 2 which is varying with time, and because it is varying with time, there will be some d psi dt, that is the induced EMF. So there will be some induced EMF, some positive induced EMF in the rising portion and some negative induced EMF in the falling portion. Zero otherwise. If flux linkage does not change, then there is no induced EMF. And so these are the four types of induced EMFs that we have studied. So first two are statically induced EMF or transformer EMF, and the last two are uh, basically a dynamically induced EMF or rotational EMF. Um, So then we started with a case study of a DC machine with some 12 slots, and in each slot we have 50 conductors put, and the number of turns per stator pole, that is the field winding, that is basically 500. So 500 turns or turns on the top pole, 500 turns on the bottom pole, and both are connected in series, and you have some 1 ampere of field current flowing through that. Now we try to see what happens if the rotor is actually rotating. So for this case, none of the stator armature windings are excited, only the field winding is excited with 1 ampere of current, and the rotor is rotating. But the current, because the current of the field winding does not change, so you can see, and the inductance, because it's a cylindrical rotor, the inductance of the coil also remains constant, reasonably constant. So you can see that the flux, it is almost the same number of flux lines that you are able to see. Now if I plot it, then this is the current, which is constant, as you can see, as I have shown with the red color, and the blue one is the flux linking the first coil or the field winding. So here you are able to see that there is some small variation. Again, mind you, this is y-axis is a zoomed in version, so the upper and lower limits you can look at, it is not from 0 to some positive value, but it is from 3.25 to 3.75. In this scale you are able to see some variation, and we understood that this variation is related to the number of slots that you have. So if you, in this case, this is data for one complete cycle, and if you actually count the number of uh, cycles of variation which are there, that is actually 12. So you have that is due to the number of slots that you have. So at this location, at this rotor position, you can see that what is the small variation that is happening. If you consider this pole, this stator pole, how many number of rotor slots are actually within this. You can see this is first slot, second slot, third slot, which the three slots which are under this pole, and the next slot openings are actually just outside the stator pole, the stator pole periphery. But if the rotor rotates by some small angle, then you will be able to see that you have another condition where actually you have 1 2 3 and 4. So 4 slots which are under this, under the stator pole. uh, so you can clearly see that it is different from the earlier case. So the because of the small slot opening, there will be some small variation of inductance. So because of that only, there is some small variation of self flux linkage of the field winding, but it is reasonably constant. It is reasonably constant. So so for this case, if you write psi f equal to LF into IF, this LF, you can see that it changes with rotor position, but that is not a very strong function. We can for our modeling purposes, it is, we will not, I told sometime before that if you have any physical system, and if you want to have a mathematical model of that, then you need to make certain reasonable approximations and reasonable assumptions. So here our assumption is that uh, although this field winding inductance changes with rotor position slightly, but it is quite small, so we can assume safely that this LF, whatever this is a function of, this is a weak function, so this is a constant value of LF. So because it's a constant value, so the flux linkage becomes LF into IF. So there is basically no change of flux linkage with rotor position, with rotation. So you can reasonably neglect the term dou LF dou theta. You can assume it or approximate it to be 0. So the only induced EMF, the only if you write the voltage or the induced EMF of this coil, induced EMF say EF, that will be only LF into DIF dt. and if you include the resistive drop also, then if total voltage applied is Vf, then it will be Rf into If plus Lf into dIf dt. So this is the equation of the field winding. So this can be represented, or this is nothing but, this equation tells you that it is nothing but a series combination of some resistance and some inductance. So this is the equivalent circuit model for the field winding, where Vf is the input voltage, you have current, and you have current flowing through that, and flux linkage is proportional to the current. So flux linkage phi f is nothing but If into Lf, where Lf is constant. So this is the model that we have got. So if you want to so equivalent circuit model already I have discussed. If you want to solve that numerically, then what you need to do, you need to have some box which is the model of the system, which will take the input, that is Vf, and output as the current, and probably you can take another output, that is the flux linkage of the coil. Then how to get that? You can simply write this equation in a different way. You have Vf equal to If plus Lf dIf dt. So you can take this Vf minus Ifrf on one side, then you can divide it by Lf, then you get dIf dt. Now if you integrate that, then you will get If equal to integration of 1 by Lf Vf minus Ifrf dt. So this is the one you will have. Obviously, if you are doing this, then you have to have some initial condition of If. So this If is the state variable of the system, which so you cannot get in order to solve for If, you need to know the all the history of application of input. So in time, what all field voltages have been applied are necessary. So if you want to know the current at tth instant, so you need to know what you need to do, an integration from minus infinity to t. For that case, you will not need this initial condition. But say if you so for this, what do you need to do? This anyway, this Lf, Rf, and If is some If is also necessary, but previous instant If basically. But you can see that um, all the history, even if that is not known, so integration, this linear, this is you can simply write it to be like this. So minus infinity to some known instance, t0, Lf Vf plus minus Ifrf into dt, plus you can I am just uh, changing the limits, or dividing the limits of this integration. So minus infinity to t0 and t0 to t, same thing, Lf Vf minus If into Rf into dt. So this thing, the first term, that will if that will tell you, that basically tells you what is the current at t0 instant. So if that is known, then this whole thing can be simply written as If at If at t0, and the other thing remains as it is, t0 to t, 1 by Lf Vf minus Ifrf into d. Because I am writing it as t, so I will use a different variable, say tau for time. Yes. uh, yes. So because t I am writing as one variable, so the running variable should be something else, otherwise there is confusion. So uh, so you can see that in order to solve for If, you need to know what is the initial, at some instant you need to know the current, and afterwards you need to know what is the voltage history from this instant t0 to t. So suppose this is time, say you have some voltage, say this is the voltage variation with time across the field winding, and because of that you want to know what is the current. Now what is the meaning of this equation is, if you know what is the current, and because of that say the current also varies. So you want to know what is this, how what is the value of current at say some um, time t equal to t1. You are interested to find out this value. So for this, what information you need to have is how the voltage varies from minus infinity to this time instant t1. So this is the basic thing that is required. But the equation tells you that the same thing can also be obtained if you know what is the current. If you simply divide this whole time duration into two portions, you have one duration from minus infinity to t0, another duration from t0 to t1. If you know what is the current at t equal to t0, that is some if at t0, if you know this value, and if you know how the voltage varies after that till the point of our interest, then we'll be able, if you know this how the voltage varies from t equal to t0 to t1, and if you know what is the value of I at t equal to t0, then with this equation you will be able to solve for um, the field winding current. So for all these simulations, we'll assume that we'll assume that initially there is no current before some. So we are starting the system. So before that there is no field voltage and there is no field current also. At certain instant we are applying some field voltage. So at that instant of starting, that current we'll assume it as because for our case the current will be zero. So uh, so this is the idea, and this can be basically modeled. This model, whatever I have indicated here, this can be realized by using some basic function blocks. So the input, so the input, that is Vf, we are simply following this equation. This is Vf. We need to subtract the resistive drop. So this is a if of the previous instant that we have to do if we are solving it in discrete system. Then obviously you have to have some gain of 1 by Lf. What you will have is V minus IFRF 1 by L, that is already done. Then you will have to use some integration block, and the integration will give some IF. So integration is the only dynamic operation that you are doing. Otherwise all the operations, so obviously this IF will come, this will be multiplied by this resistance RF, and this is your system. So this becomes your system, and if you want to solve for psi, you can simply multiply it with LF and you will have your psi F. So those are the two outputs that you want. Or psi F is also okay, psi F can be obtained by this. So you can see in this operation, in this block diagram, this gain does not need any history. So any gain, if you know the input, say u1, you immediately know what is going to be the output y1. So this is simply related by the gain term. So y1 equal to k into u1. So this is a static equation. So this multiplier things or the gain blocks, they are static operations. So What do you mean by static operation? You need not only if you know the input at t equal to t1, you can know the input, you can know the output at t equal to t1. But the only dynamic operation that is coming, that is this integration. So for integration, you for getting the output, only that instant current is not enough, or that instant input is not enough for you to tell what is going to be the current at that instant, but you need the input history. You need the input history of starting from infinity, or you can define some initial condition of the output, and if you know the inputs afterwards, then you will be able to solve for if. So if you go inside the integration block in MATLAB, you will find that you will be having some option to define the initial condition, initial value or initial condition. Something will be mentioned. So you need to set it as 0. So idea is, when simulation is starting, your starting current is 0, and afterwards, with the input of with the application of voltage, there will be some change in current. So this is how to simulate uh, the field winding. This is how to first model the field winding, then how to simulate that in an environment such as Simulink. Or you can also do that by writing equations, and this integration and other things can be done in a discrete fashion using some numerical techniques such as forward Euler, backward Euler, trapezoidal integration. All those things you can do. So basically, your Simulink is doing some numerical integration um, to solve for whatever you are doing. You can also define that yourself and write your own thing. Now next we will discuss, uh, we will go to the armature coil, and how the flux linkage varies, of armature coils with rotor rotation. So the assumption is the flux or the field winding, that is always excited with some constant current. So that is also having some constant flux linkage, but we are having so many different coils. So we are having this coil 1 indicated by orange color. Say this one side is this is of dot polarity, another one is of cross polarity. So in this case, what is the thing I have taken? So whatever, so probably this is dot and this is cross, because if this polarity current passes through the winding, then it will produce some flux in the downward direction. And actually, if the flux is in the downward direction, or I think it is dot and it is cross, because as you can find here, the orange curve, initially at t equal to 0, the flux linkage is actually negative. That means the polarity must be opposite. It must be dot and cross. So it means that if some current would be there, then it would produce some flux on the up direction, in the upper direction. But actual flux that we are having, that is actually, what was the direction that we are having? Did I mention it anywhere? Okay, I did not mention, so I have to assume something. So probably, what is the thing we have been considering? We have been considering the red one to be dot and the black one to be cross. So the flux will be upward. So that means the first thing that I told you was actually correct. So the reference direction is actually uh, dot here and cross there, because initially that basically is coming from the initial flux linkage sign. Initially flux linkage is negative for the first coil. So That means because our dot and cross of the field winding is like this, red one is dot and black one is cross, so the flux must be on the upper side, upward direction. So that means the polarity, the reference polarity of current for the coil 1 must be cross on the left side and dot on the right side, so that if positive current flows, then um, then it would be downward side, but the actual flux is upward. So that is what we discussed last year also. This is about the reference direction. So so this is what we are looking at. We are looking at different coils. We are having, so if any number is indicated without this dashed, that you consider it as dot, like all these are dots, and if a number is indicated with the dashed thing, then that is basically cross. So this is our reference for this case. So what I am plotting in the right hand side case is how when the rotor is rotating, how the flux linkages of these different coils are changing. So here we have 12 slots. So we are considering single layer winding. So single layer winding means you have two sides of a coil. If we have two sides of a coil, so one side is there, is occupying one slot, and the other side is occupying another slot. So this coil one side, the one dashed, that is occupying this slot, and another side the one is occupying this slot, and one dashed is occupying the diametrically opposite slot. So 12 slots you have. So that means you can house 12 coil sides, because it's a single layer thing, single layer winding. So each coil will have two coil sides, so the number of coils in this case is 12 by 2 is equal to 6. So we have 6 coils. We are looking at the flux linkages of the 6 coils as the rotor is rotating in the anti-clockwise direction. So uh, I think I have forgotten to put that animation, but anyway it is the same animation as this one. It's the same animation as this one. As the rotor rotates, uh, what are the flux linkages first, and then what are the induced EMFs of these different coils. You can clearly see that initially when it started, the orange one, that is the coil 1, that is having maximum flux, that is having flux linkage peak. All the flux lines are linking that, all the flux lines are linking the orange coil. But the blue coil are also linked by almost all flux lines. Red coil, certainly some flux lines are not linking that. Suppose uh, if I indicate this flux line, say some flux line like this is surely not enclosing either of the red conductors. So red conductor at that instant, at the same instant, certainly will have less flux linkage compared to the orange one and the blue ones. Then if I talk about the pink one, all the flux lines, if I indicate one flux line on this side, certainly this is not enclosing the pink conductor, and similarly the other side flux line, the very next flux line, that is also not enclosing the pink conductor. That means for this rotor position, the pink conductor is actually having zero flux linkage. Again, the brown conductor, there will be some again there will be some so the flux linkage sign will be opposite, same as red one. The brown one will be having the same flux linkage, but sign of the opposite polarity. Again, green and blue will have same flux linkage, sign of opposite polarity, opposite sign basically. And again, the this is the same coil side. So this is how the flux linkages of different coils you expect to find. So if I stop at instant 1, you can see that uh, the first coil, that is orange one and blue one, they are having almost the same flux linkage. Then for the red one, you are having reduced flux linkage. Pink one, you are having zero flux linkage. And brown one, you are having again a positive flux linkage, and that flux linkage value, the magnitude, is same as the red flux linkage, only the signs are opposite. And again the green one, you will have some positive flux linkage, and that is having same magnitude as that of the blue one. So this explains you what are the linkages of the 6 different coils at this instant 1. Then if I then go to instant 2, so the rotor, as you can see here, uh, uh, the orange ones are horizontal. Now at the next instant, the orange ones are actually vertical. So that means it has rotated by 90 degree. So if total rotation takes 40 millisecond, considering 1500 rpm, then 45 or 90 degree will be rotated, or it will rotate 90 degree in 10 seconds, 10 milliseconds. So this dotted line indicates the next instant which we are looking at. So at that instant you can clearly see that, so how was the polarities. So this was dot, this was cross. So this will rotate. So this one will be dot, this one will be cross, this one will be dot, this one will be cross, this one will be dot, this one will be cross, dot, cross, dot, cross, dot, cross. So these are the reference directions. Now you can see that the flux line direction is actually upward. So the flux linkage of the pink coil for this instant is actually positive, uh, because the reference direction of winding, that is actually dot and cross like this. So had there been any current, the flux due to that would also be upward. So the actual flux is matching the direction. So that is why the pink one is having um, maximum flux link, or maximum flux linkage at this instant, as indicated here. Now what about the brown one? So the very next one, say the brown one, that is also having positive flux linkage of almost the same magnitude. What about green? Green is also having positive flux linkage but of reduced magnitude. The magnitude has reduced a bit. What about orange? Orange is having zero flux linkage. Orange is having zero flux linkage. So again, if you go to blue, blue is also having positive flux linkage. So blue, yeah, blue had, I think blue, have I discussed just before this? Yeah, blue is having blue, red, and uh, uh, this. So this red, where is this red? So this red and brown, they are also having almost positive, almost the peak flux linkage. All are same as that seen by the pink one. And again the blue and green, they are having equal flux linkages and of the same sign. And the pink one and the this orange one, that is having zero flux linkage at this instant. So same thing you can do for all the other instance also. So this is how if the dotted line moves with rotor rotation, the waveforms tell you how the flux linkages, how the flux linking the different coils actually change. So uh, so here I have plotted the flux linkage of coil 1 and coil 4 only. and I intend to show what is the induced EMF. So you know there is induced EMF is time derivative of the flux linkage. So here flux linkage is changing. You can divide it into different portions, different intervals. So probably this interval first is 0 to this interval, so T1 to T2, then all this while it almost remains it keeps on ramping almost linearly, so T2 to T3, then T3 to T4, T4 to T5, and T5 to T6. So these are the instants. So you can see between T1 to T2 the flux linkage remains reasonably constant. So uh, the induced EMF will be 0. Between T2 to T3 the flux linkage rises linearly, so the differentiation will be a constant number. So it will have some positive induced EMF. Again between T3 and T4 the flux linkage is almost flat, so there is almost no induced EMF, zero induced EMF. Between T4 to T5 you have the flux linkage that is falling again linearly, so because of that the induced EMF will be negative of the same amplitude, because both are having the same, almost the same slope. So this is the induced EMF between T4 to T5, and again T5 to T6 the induced EMF will be 0. So actually if you have access to the coils of a DC machine, then you will be able to see that the induced EMF of the coils will be this quasi-square wave. So if you have a periodic thing, so this is 0 to 2 pi and this is pi, so this something positive from 0 to pi and the negative from pi to 2 pi, that is what we is known as perfect square wave. But if it is square but it has some zero durations in between, such that this type of waveform is known as quasi square, because uh, it is square but you have some added zero durations in this. So the actually if you see the induced EMF of a coil in a DC machine will be of the shape quasi square wave, which will have both positive as well as negative um, flux linkage, negative induced EMF. So next if I try to do the same thing for the psi 4, then 0 to this is one instant, say this is again T1, then I have to use T7, T8, T9, T10, and this is same as T6. So if I draw the induced EMF, it is obviously it is ramping between T1 to T7, so it will be some positive value. Between T7 to T8 it will be 0. uh, T8 to T9 it is all the while ramping down, so some negative value. T9 to T10 it is at 0, and again T10 to T6 this is again a positive value. So if you compare these two waveforms, you'll be able to see that these are just shifted versions of each other. So the flux linkage is because the different coils, they are actually shifted in space with respect to each other, so the flux linking them are also shifted, as you can see in this waveform. These two, the pink and red one, they are simply shifted by this much time, and if you convert it to angle, it will be related to whatever is the angular difference between these two. If this is a two pole case, this is a two pole case, so whatever this angle is, so this angle is 360 degree divided by 12, so that is 30 degree. So here also the flux linkages of these different coils, they are phase shifted by 30 degree from each other. And similarly, if I look at, because I have taken flux linkage of coil 1 and coil 4, so coil 1 is here, and coil 4 is actually horizontal for this time instant, so they are 90 degree shifted with respect to each other. That is why you can see that uh, yeah, the peak of the second one and the peak of the first one, if you look at the shift between the two, that is exactly 90 degree from 10 to 20. So that means 1/4 of the total period, so that means the angle displacement is 90 degree. And because the flux linkage waveforms are shifted by 90 degrees, so the induced EMFs are also shifted by 90 degrees. So if you want to represent the coil, one single coil of the DC machine, one, if you want to represent, you will, if you want to represent, you will have, you will want to represent all these coils separately. So if I pick out only this coil, say the pink coil, so the pink coil, if you want to represent the dynamic equivalent circuit of that, then obviously you will have to, it will have some inductance, say R A, so the, say pink one is coil 4, so R L A 4. And the inductance, you can see the pink coil, if you consider the pink coil, the axis, I will go back probably here. So the pink coil axis was horizontal here. Now as it has moved, the axis becomes vertical. You can clearly see that the air gap path is very different along these two different axes for the pink coil. So if you actually have to represent the pink coil, the inductance, that will be a function of rotor position, and also you will have some resistance. So how to represent that? You will, if the voltage is VA, then it will be some RA4 into IA4, plus you will have this LA4 as a function of theta into DIA4 dt, plus we will also have the dynamically induced EMF, that is due to variation of its own self inductance. So you will also have to put A4 into dou LA4 as it varies with rotor position multiplied by omega. So the equivalent circuit for this case, you will have to put the resistance similar to this SRM case, SRM winding. You will have to put uh, the resistance, the self inductance, as well as the back EMF. That is how you, if you want to represent the equivalent circuit of one coil, if you want to represent that, then this is how you will have to do that. And this will be equal to IA4 into dou L A4 dou theta into omega. This is how you would have to do that. But you know that in for armature coil, the entire armature coil, we simply so this inductance actually does not vary. Inductance remains constant. Inductance is actually constant number. Then we use some resistance, and we use some constant back EMF. So how do we get that? Actually, if I whatever I have discussed till now, it is very clear to you that if the rotor actually rotates, and if you look at the induced EMF of the individual coils, that is a bipolar thing, that is having some positive induced EMF, positive voltage, so at some rotor positions, and it has some negative flux linkage at certain other rotor positions. But actually, you know, at least in the steady state case, how do we represent the equivalent circuit of the DC motor? We armature, we put some resistance, we put some constant back EMF. Why is it a constant? How can we represent this with a constant? So that is the next question that we are going to deal with. So for that, it is important that uh, we understand how these different coils are actually wound, and how the coil terminals are actually taken out to the external world. So we are very clear that internally, if we look at any individual coil that is having some positive, that is having um, induced EMF, sometimes positive, sometimes zero, sometimes negative. But because of the winding connection, the armature uh, winding connection, along with how it is connected, how it is brought out extra to external world through commutator and brush, that actually causes the induced EMF to become a reasonably constant number with rotor position, and the inductance also becomes a constant number. So that is the next topic that we are going to um understand. So for that, we need to understand how probably a sample example of how the armature winding is wound, and how it is actually connected to the commutator, and how uh, the commutators are connected to brush, from which we take the windings to the external world. So it is like you have something, you have rotor. This is how your rotor looks like. So for the all the terminals, so this is one coil, so this is one coil, these are two terminals. Similarly, you have so many terminals, so all these terminals will be, and all this is rotating. So the rotor is rotating, the coils are also rotating, so the terminals are also rotating. So but you have to take these terminals to the external world, that is static. So how to do that? So what is done is, you have this rotor, you have these windings, say rotor windings. So one coil, second coil, third coil, and these are coming as different terminals. So you have, on the same shaft, you have another thing called as commutator, and these commutators are having some segments. So what is the meaning of these segments? Segments are basically, so uh, you have so this is a copper thing, and whatever these lines I am drawing, these are insulation. So this internally, this portion, this entire portion is copper, and again this entire portion is copper, and these two segments of copper, they are insulated by some insulating material in between. And the different coils are actually coming and getting connected to this copper segments. So these are called as the commutator segments. So all the terminals of the coils are actually coming and getting connected in some of the segments. So both of these are rotating. So the armature rotor is rotating. Armature coils, that is the rotor coils, are also situated on the rotor, so they are also rotating. And all the rotor terminals are connected to this commutator segments, and the commutator is also rotating. So this entire thing is rotating. So how do you connect, how do you take connection? So all these things are rotating, but your external coil, that is, you have to bring the connection to your physical to your external world, that is static, that is not rotating, at least with respect to earth. So you will have to place some brushes some brushes on this commutator segment, and your actual winding two terminals will be coming out from that, and this will be pressed on these commutators. So the commutators will be rotating, and these brushes will are static. So this commutator, some commutator segments are shorted with this brush at certain instant. For certain instant, some two side by side commutator segments are also shorted together. So those will understand. But finally, you will have whatever induced EMF are there in the different coils. Those will be added or subtracted because of this winding connection through these commutators, and finally you will see to the external world, you will see what is the voltage across these two terminals. So that is the voltage that we'll be looking at, and you will eventually find out that this will be, although these internal induced EMFs, all these internal induced EMFs of these different coils, those are quasi-square wave type, but this internal induced or the external induced EMF, what is visible from the two terminals from here, we'll find out that will be a constant DC quantity. And also similar to that, all the coils, if we look at all the coils, so say this is a coil, this is an armature coil, the current say IA1, and this is say coil 1. So if you look at the current waveform, of any coil, it will be like because the voltage, the induced EMF is something like this, quasi-square wave. So you will find that the current of this coil will be positive when the induced EMF is positive, and it will be negative when the induced EMF is negative, and it will change its polarity at the middle, and this is how actual the currents, the IA1 or the other coil currents will be. This is how the coil currents will be. But because of the winding connection and because of how they are connected through the commutator and brush, you will find out that to the external world, whatever current is being injected, that is the net armature current, that will be a reasonably constant current. So we'll be able to understand how it is happening once we discuss about the armature winding. So let us briefly start with that. So the basic idea is, so you know this, so for the case that we are dealing with is a 12 slot armature or rotor. We have a 2-pole case, and it is a single layer winding, and the winding can also be two types. It can be lap winding or wave winding. We will discuss this lap winding only, and there is something you will need to know what is the number of commutator segments. Number of commutator segments, as we will find out, that is same as number of coils. So whatever will be the number of coils, that will be the number of commutator segments. So by commutator segment, what we mean, we have this commutator, this ring, how many different segments are there. So say this is the case where you have 4 segments. If I again make some insulation thing, you will have 8 segments. So like this, how many segments to be kept, that actually depends on the number of coils that you have. So how to determine the number of coils? It depends on how many slots. So how many slots you are having, and what is this winding pattern, so single layer or double layer. So if you have single layer, then the number of coil sides is same as this is for single layer. Number of coils is equal to number of slots. So in this case it is 12. So the number of coils is half of number of coil sides, that is 6. So in this case, for this 12 slot and single layer winding, we'll have 6 commutator segments. But had it been double layer, what is double layer? If we have one slot, one armature slot, so this is one armature slot. For single layer, the entire slot will have only one coil. But for double layer, the slot will have two layers of winding. First one top layer and one bottom layer. So that is what is double layer winding. So for double layer winding, the number of coils or number of coil sides, that will be twice that of the number of slots, equal to 24, because in each slot you can actually house two coil sides. So the number of coils will be half of number of coil sides, that is 12. And same will be the number of commutator segments. Now next we will have to decide what is the number of brushes. That is how many brushes we have to put. So that depends on, so that is related to what is the number of parallel paths, in your winding. So that depends on what type of winding it is, whether it is lap winding or wave winding. So if it is lap winding, the number of parallel path, commonly referred to as A, that is same as number of poles. So for this case, if you are having lap winding and two poles, so number of brushes will be 2. But if it is a wave winding, then A is always equal to 2, so the number of brushes will also be 2. This is 2 for all cases for wave winding, but for lap winding it is equal to number of poles. So this is a specific case where you have 2 poles, so that is why for this example case we will have 2 number of brushes. So let us close here today. Next day we will start with the discussion on armature winding and how actually although we have quasi-square wave voltage induced EMF waveform and we have pulsating current waveforms into each coil, we will understand first the armature winding, and then from there onward we will go on to understand how the net induced EMF of the armature coil, that is reasonably a constant value even with time, and how even if we see that for individual coils as it rotates, the inductance changes. So the inductance is actually changing, but still for when you are modeling armature winding, as you have solved for individual cases for your machine parameters, you have looked at them, you know that that is typically a constant number. So this LA, that is whatever is the inductance of this entire coil, that is a constant number. So we will understand uh, how that is so. Okay, is there any question, Hugh?
No, sir.
Okay, so let us stop.